Okay, I'm going to cover sections 2-6 through 2-8. First law of thermodynamics. Okay. Basic idea is energy can't be created or destroyed. All it is you can transform it from one form to another. Okay. And here's a couple of examples. In this case, you have a boulder up on a cliff and it has some potential energy associated with it, and that potential energy is 10 kjoules. And in this case, we assume that wind resistance is negligible. So it has no kinetic energy at this point because there's no motion. And as it falls down, what happens is the potential energy goes down and the kinetic energy goes up. And as long as, just prior to hitting the ground, all of the potential energy will have converted to kinetic energy. And then when it hits the ground, of course, that energy is transformed into heat and sound, essentially. Okay. Here's another one. Put energy into this potato, say, right? A certain amount of energy, and the boundary is like the outer shell of the potato. And when you do that, whatever or put heat into it, it changes the internal energy in terms of heat inside the potato. Okay, so you only transfer from one form to the other. Okay. Okay. Continuing on. Now we have, let's say this is a pressure cooker. You have a certain amount of heat coming in. You get a certain amount of heat change in internal energy, and you have some heat leaving. Okay, so what you're going to find, of course, is the change in internal energy, which is the change in heat energy, essentially, is equal to the difference between these two. Okay. Now, when we look at an adiabatic system, in which we basically have no heat, entering or leaving through the boundary, we have work being done by heating of an electrical element, a resistor, and we get a change in internal energy due to that. Okay, an increase in heat, essentially. Okay, but we could just write it as, in general, as delta E. Same thing here. We're doing work on the internal fluid in here, and we have a change in internal energy. Okay, and both cases, these two cases, we defined it as adiabatic. Perfect insulator. So we can quantify that and come up with an equation. Total energy entering the system is equal to total energy is subtracted from the total energy leaving the system, gives us the change in total energy in the system. Okay, so we just write it as E in minus E out equals delta E of the system. All right, and here's a couple of examples. In this case, defined as an adiabatic system. Do some work in, causes a change in energy, internal energy. Okay, and then this case, it's not adiabatic, so you have work being done here, heat being added. We take the work and add it to the heat, and we get a change in internal energy. Oh, sorry, we subtract out what's leaving in terms of heat, and we get a change in internal energy due to that. Okay. Now, if we also take into account the kinetic and potential energies for a system, we can come up with a total energy change to a system. So we'd have delta E is just going to be equal to, this is another way to write this, whatever change in internal energy, whatever change in kinetic energy, and whatever change in potential energy. So if we add these all together, we have the complete change in energy. Okay. Now, here's our change in internal energy, would just be the mass times whatever change in internal energy, or sorry, energy per unit mass. These are energies per unit mass. Okay, and then in this case, here's our kinetic energy. These are our velocities. Okay, the initial, the final velocity squared minus the initial velocity squared, and then here is our change in potential energy. Okay, and these are like the vertical positions. Okay, so this is the difference between those two positions. All right. Now, if the system is stationary, the potential energy and kinetic energies are equal to 0, and then we're back to that original equation we had where delta E equals delta U, or the change in internal energy of the system. Okay. So what we're going to find is that here's the mechanisms for this energy transfer. We have different forms. We can have heat, we can have work, and we can have mass flow. Okay. Now, a system's considered to be closed. That means we will not have any mass flow. We only have heat transfer and work. Okay. But here's the general form of the equation. We're going to see this difference in change in internal energy of the system. Okay. It's just going to be basically, or I should say, change in energy of the system. The change in energy of the system is any change in heat energy, the change in work, work in minus work out, heat in minus heat out, and then mass in minus mass out. Okay. Any other note to make of this is, of course, if what they say is, the energy interactions are basically defined at the boundary of our system, okay, which you define. All right, and like here's the dashed line that represents essentially the boundary in this example. Okay. So we can also represent these as rates, okay? So if we wanted to know like the total heat, we would have a rate at which the heat is being transferred times its time, okay? And here's the same thing with work. And we could also come up to see at any point in time essentially the rate of change, okay? In this case, typically defined as delta E over delta T. So this is, of course, the differential form of that, okay? Now, if we wanted to write it in terms of change in energy per unit mass, we would write it just like this with lowercase e, okay? And the same thing here, if we wanted to put it in a differential form, we would do it as the delta E, delta T, so that this is just saying, like, if you had this small incremental change in each, you could actually come up with a small incremental change in terms of the internal energy of the system, okay? And same thing per unit mass, right? So here's one example. We have a mass coming in, mass leaving. So the energy interactions are mass in minus mass out, Q in minus Q out, and work in minus work out, okay? We'll also look at cycles. Essentially, cycle is just going to be, it just sort of goes around, back and around. It returns back to its previous state, okay, in terms of pressure and volume. Okay, so we'll look at this some more. All right, so with a cycle, the total change in energy is 0, and then essentially heat is just equal to Q, okay, or the net that. I'm sorry, W equals Q, or the heat equals the work. Okay, continuing on, now we're into energy conversion efficiencies. Okay, so efficiency is just how much energy conversion or transfer process is accomplished, okay? And really what we're going to see is like how much useful work we can do from the actual energy that we used, okay? So we could divide this as like performance, desired output over required input, all right? And one of the things we're going to find is that you can't have a system essentially that has an efficiency that's greater than 100, all right? Okay, so in this case, here's some typical efficiencies for water heaters, right? So what we're saying essentially is that the amount of heat, that you'll actually transform to heating the water is, so if you put like over some period of time, you could do it as a rate, or you can just do it as like a total energy or total heat. it would be, you know, whatever energy you put in would be down here, and whatever you got out would be up here. Okay, so what you're going to find is, of course, this is going to be less than the numerator is going to be less than the denominator, and that's essentially what you're getting here. Just multiplying times 100, this ratio times 100% will give you these numbers. Okay, so you can find, like in this case, oh, electrical high efficiency is most efficient, all right, in terms of energy transformation. Okay. Okay. Now we can also look at this in terms of combustion efficiency. So this is just a ratio, and like if you wanted to turn it to percentages, you would have to just multiply it times 100. But if the heating value of the fuel, this is if, like it says, if the fuel is completely burned. So it's like energy content of fuel would be predefined. Of course, you're not going to get 100% of the energy released, right? From that, you're going to always lose some in that combustion process. Okay, so you just say that this is the amount of heat that's released during combustion, and you can actually come up with an efficiency measure for that. Okay, and you'll see this nu is used as the symbol for efficiency. And just some other terms, we have a lower heating value and a higher heating value. Okay, and it's just defined as if the water leaves as a vapor, or in this case, the water in the combustion gas is completely condensed, and thus heat of vaporization is also recovered. Okay, so just some additional terminology as we look at different problems. Okay, so here's like an example. You have some combustion gases leaving. You have a combustion chamber, and in this case we have here's 44,000 kilojoules for kilogram, and maybe you have a kilogram of gasoline. Okay, just to show you like a quick example of that. So one of the terms you'll find, or the acronyms is AFUE, you find for residential systems, heating systems. And what it accounts for is some other things that are lost. Okay, combustion efficiency and losses such as heat losses, unheated areas, and startup and cool down losses. Okay, but this is a common term or common acronym that's used, or metric, if we want to call it a metric, annual fuel utilization efficiency. So that's just some basic terminology for fuels that are combusted. In that case was gasoline, it showed in that example. We also have other things. Generator efficiency. Okay, generator is just a device that converts, from mechanical energy to electrical energy. Essentially, this is where our electricity is coming from at a power plant. It's being generated through a generator, right? Okay, so we also have generator efficiency and thermal efficiency, okay, to take into account. So, if you're talking about how much energy, let's say in the power plant, that's actually coming in to the power plant, what you're going to have is you have to think about at each stage along the way. You have combustion efficiency, you have thermal efficiency, and generator efficiency. And to get the overall efficiency, where you have the overall efficiency of the whole system, you have essentially, you're in this case, you're losing, you're not converting all of the fuel over to like mechanical energy. In this case, you're losing heat along the way, and then the generator itself has some loss in efficiency. So you'd have to multiply these all together to talk about the overall system. Essentially, what's your output divided by what's your input. Okay. So you have to include all these. So this is one way to look at it. You could also talk about, this is the rate equation, and this is the essentially the HHV times the mass, the net mass rate. Okay, this is fuel. Okay, so this is what's coming in essentially, right? The rate that fuel is essentially being consumed, and in terms of its energy, right? So it's essentially energy rate coming in of fuel, and this is the electrical work out rate. Okay. Okay. So this is like a rate, or this would be energy per unit mass, and then this would be like the rate at which it's coming in, rate at which it's being consumed. Okay. All right. So we also have lighting efficacy. All right. And we'll also look at efficiency, but this is the amount of light you're actually producing per watt of electricity. Okay. Now, if we take a look at this and think about light bulbs and different types of light bulbs that we see out there, a higher number is going to be better, right? So you produce more light for the same power that's being consumed. And what you're finding is that, like, fluorescent here, and it doesn't look like we have LEDs here. Nope. So for fluorescent lights, you actually produce more light output for the same power. Okay. Now in the past, you'll see we have bulbs that will be listed wattage output, which is really just the energy that's being rate at which energy is being consumed, electrical energy. And we can compare it to these two lights. Essentially, going to give you the same amount of illumination, okay, or lumens, okay, you can say. Okay, we can also look at it in terms of appliances. All right, in this case, we're talking about heating or cooking appliances, and if you're talking about how much energy to be consumed to actually get it up, this is just some examples, of course. How much energy or how much cost? What would you find in terms of total cost of energy? Of course, it'd be very specific. So this is a very specific table. And these are some examples, like for that temperature, how long it's going to take, how much energy you consumed, and the total cost of the energy. Okay. And in this case, it's casserole that they're cooking. All right. So what we're finding here, of course, is that microwave oven is actually the most efficient in terms of that, and the quickest. May not come out the best, but that's your trade-off. Okay. And efficiency here is just energy utilized over energy supplied to appliance. And one of the units that we'll use for energy, total energy, is the kilowatt hour. Okay. So it basically means, like, in this case, for example, maybe you have a 3 kilowatt appliance, so 3 kilowatts of energy is being transformed, and you do it over 1 hour, you get 3 kilowatt hours, essentially. Okay. Or it could be, 1.5 times 2 hours, however. But this is total energy. All right. So just some things to keep in mind. Energy efficient appliances conserve energy, right? So if you use more energy efficient appliances, of course, it takes less energy down at the power plant to actually perform, the action of cook, in this case, cook the casserole with less amount of energy. So as a result, you get less combustion of the fuel, potentially, unless it's like a hydroelectric plant. But if it's a coal-fired or a nuclear power plant or oil plant, then of course you have this. But okay. Okay, we can also look at mechanical energy. So in this case, it's like whatever output over input. You could also write, in this case, it's mechanical output or mechanical input. Or you can just rearrange this equation, and it would just be 1 minus the mechanical loss over the mechanical input. All right. Because this term here, of course, this 1 minus this, if we took this term and just said instead of the energy mechanical out, if we put that in terms of in minus the loss, right, then we could rewrite that. And then, of course, it's going to be in over in, gives you the 1, and then minus loss over mechanical in. So that's a different way to represent that. Okay. We also can talk about pump efficiency and turbine efficiency. All right. And same idea. The mechanical energy of if you're pumping something divided by the mechanical energy of input. All right. So the rate at which you're, like, maybe you're lifting a fluid up, the rate at which you're moving that mass up, and the energy, the addition of the potential energy or kinetic energy. If it's just lifting it to a higher position, then you would have just potential energy. Depends upon how you're going to define it. All right. But you could write it in terms of maybe the kinetic energy and potential energy. So this could be kinetic and potential energy, and that's divided by the total, like, energy put into it. If it's an electrical pump, let's say, okay, how much electrical energy came in. Same idea with like a turbine. Okay. All right, how much energy actually went in. Okay, or the energy output defined by whatever. In this case, maybe this is a turbine. It could be a wind turbine, or maybe it's a turbine in a hydroelectric dam, or some other. Yeah, well, we'll think about it in those terms. A hydroelectric dam or like a wind turbine are good examples. And here's the mechanical energy decrease in the fluid. So this is kind of like the energy coming in. Could be wind energy. Okay, and this is the actual wind energy output, right? How much energy output you can get to turn that turbine. Okay. Here's a fan. So a fan is a nice example. So you add work in to the fan to turn the blade, and that adds essentially kinetic energy to the fluid, or in this case it's going to be air. Okay, so you have some zero velocity in the end you have, for this particular example, so what you're getting is just essentially increasing the kinetic energy of the air. Okay, so we write it in general the same form, change in energy. So this just becomes essentially just the rate at which mass is flowing, and they've already defined it here as 0.5 kilograms per second, times the velocity squared over 2. And here's the actual work that came in. In this case, it was 50 watts. So the equation just becomes, that rate at which the mass flow rate of the fluid, in this case air, times the change in velocity. In this case, it was 0 initially, so it's 12 meters per second squared over 2. Divided that by our 50 watts, and now you come up with a mechanical efficiency of this fan is 0.72. Okay, so you can go through the same kind of idea for pumps, generators, pump motor, also turbine generator. So in this case, like if it's a wind turbine, what is the turbine turning? It's turning a generator, right? So we have efficiency or energy losses in each of the steps. Okay, turbine generator. And this is a pretty common thing, right? Because you'll have a turbine. It's connected to a generator, either like I said, through wind turbine, or hydroelectric dam. Also is another example of that. So the actual efficiency is just going to be the product of the two. Okay, energy and the environment. So one of the notes here, of course, is if it often affects the environment. Okay, when you make that conversion, energy from one conversion to another. If it's our, when you drive your car, if it's a gasoline powered car, you're going to get some pollutants and other gases that are bad for the environment are going to be produced due to that conversion. Okay. These are some of the things. So if you're burning fossil fuels, you're going to get smog, acid rain, and some global warming to those, CO2. These are CO2 being added to the atmosphere and um, other greenhouse gases. Okay, but if you had something like a hydroelectric plant or wind turbine, of course you're not actually going in producing any gases into the environment due to combustion, because there is no combustion. Of course, there are other issues that you have to think about too, but at least from that perspective, you're not producing these greenhouse gases. Okay. Okay, some more terminology for it. All right. Some of the things that are produced like a combustion, you said nitrous oxide. Well, smog. You get smog just from the combustion of hydrocarbons. Okay. And these are talking about kind of what happens just in general, what it is. Okay. Hydrocarbons and nitrogen oxides. Okay. And these will actually form ozone. Okay. So just talks about a little bit about what ozone can do to your lungs, causes problems. And this is what the symptoms of this from this damage. Okay. So pretty bad. All right. Other things, carbon monoxide. This is bad. Of course, this can kill you. Okay. And this is one of the things that's produced by cars or from the combustion process. Right. And talks a little bit about carbon monoxide here. Okay, so it deprives body's organs from getting enough oxygen. So carbon monoxide detectors are really good things to have in your home, of course. So just talking about that a little bit more and what are the issues that result from that. Okay. And this is just talking about like ground level ozone. All right. Okay, acid rain. So acid rain, basically, mainly due to the sulfur dioxide. Okay, coal, from burning coal and certain types of coal, high sulfur coal. You also see some contribution due to motor vehicles. Okay, and here's just examples. So this is more qualitative stuff, issues that come about due to combustion of fossil fuels. Right. Okay, greenhouse or global warming, greenhouse gases. All right, and here's the main point of that. Greenhouse gases are basically gases that allow solar energy to enter freely, but blocks it from leaving. Okay. Okay, and then so it just causes an increase in interior temperature, right? So what you see is a slow increase or potentially climate change, and there's some debate about that, I suppose, what's causing it. Although we do know that there has been a general warming of the planet, okay, in recent history, right? CO2 is a primary component for this, but we have methane and nitrogen oxides also have the same kind of impact, right? This is a natural byproduct of burning fuels. Okay, coal, oil, natural gas, really doesn't matter. Wood. Okay, and a little bit more on global warming. Okay, so a 1995 study was done. They found that Earth has warmed about 0.5 degrees. And this is in 1995, of course. Don't know what the estimate is now up to that point. But since we're 25 years later, they expect it's going to go up by 2 degrees C by 2100. And assuming that things don't change drastically. I guess if we go follow the same path, all right, what you're going to see is, some severe changes in weather patterns due to that, okay? One of the things is you're going to see more melting of the ice at the poles and, shrinkage of glaciers. With that, you get some rising sea levels, all right? Well, how can you put this off? Well, put more, invest more, of course, into renewable energies, wind, or maybe solar, or hydroelectric plants. Okay, this is pretty bad. I don't see cars producing that much. Probably take it off the road at that point, right? Okay. So it just gives you an idea of, at least for an average car, okay, how much, if on for example, if you went 20,000 kilometers a year, what's that, about 13,000, 12 to 13,000 miles, and you consumed 2,300 liters of gasoline, you produce about 2.5 kilograms of CO2 for every single liter, okay? And that's pretty much it for this chapter. So that's like a quick overview of most of the main points in this particular chapter. All right, that's good. Okay. Oh, and just remember when we went through this, so the macroscopic, we had kinetic and potential, and then internal energy. So if you wanted to, you have to both have the macroscopic and microscopic changes in internal energy. And what we said, if a system is stationary, then these two are essentially zero. Okay. We looked at transferred heat, transfer work, different kinds of mechanical forms of work. First law of thermodynamics, the energy balance, right, and then energy change. So it's like you have to think about, we have to essentially account for all the energy in the transformation, right? It's going to be heat, or work. When you transform or change in internal energy, I should say, you have a change in internal energy in any work that you've done. Okay. Let's see. Oh, then we had the different mechanisms, right? So we had heat, work, and mass flow across the boundary. These were ways of energy transfer. Then we looked at efficiencies, right? So the basic idea is every time you go through a transformation, you're losing energy typically to heat out into the environment. So it's always going to be less than 1 of an efficiency, right, at each stage. And then impacts, right? Energy in the environment. What are the impacts of burning fossil fuels? Okay, and that is pretty much it.